and the red line is backscattering from the sulfur. The green one is also the same. The difference between the red one and the green one is just the compound environment. That means for the green one, these 4 atoms is sulfur. For the red one, 2 atoms is sulfur, 2 atoms is nitrogen. But you can see they are also almost the same. And the blue one is nitrogen. So you just from this, you can distinguish one is sulfur, one is selenium, one is nitrogen. They are different. For the phase shift, because we have this term, delta here, we just mentioned about this one, Fj. It's a backscattering amplitude. Then we move to this phase shift. Then we'll go to discussing about the Bywater factor. For the phase shift, the central atom are all nickel, so the phase shift is the same. Mainly differences come from the backscattering atom. So selenium is blue line, and again sulfur is you have 2 different environments, but the sulfur atom gives the same phase shift, and the blue line is nitrogen. So atom type the same, they give the same phase shift, but different atom type give a different chance of phase shift. And so you combine the central atom and the backscattering atom, actually majorly from the backscattering atom's contribution. Okay. So now we go back to see what the influence on the spectrum. If phase effect, if this I generate a sign 2k times because the distance between nickel to sulfur is 1.8 angstrom, and you have sine wave. If you have phase shift, it will go to like this. But in the equation, you have phase shift, but the phase shift is depend on k. So your spectrum will become like this. Then, if you have 2, one atom is located at 1.8 angstrom, is nitrogen, and one atom is located at 2.2 angstrom. Let's assume it's a sulfur. So you have the red line is sine. The red line is for contribution of nitrogen, and the green one is the contribution of sulfur. If you combine this, you get this. Okay, so if you find your spectrum of 10 like this, you can imagine at least you have 2 kinds of different distance. Can you understand what I mean? If you have only one, you just have the frequency is the same, only one. If you have 2, then you got this one. So actually, your experimental data will become like this, but from this you already can understand you have at least you have 2 type different absorbing and the backscattering atom distance. And let's consider the phase shift effect, and you will get this. Okay, and in here, in this equation, you have to divide by k. And this k is the effect of this k. Then it will be like this. Well, you at the beginning, at least your amplitude, but once you divide it by k, and because it's a k space dependent, your spectrum will like this. So with high k, the amplitude will go down very, very quick. That's why when you want to do acceptance analysis, we will quite often will times k cubic, and then you will emphasize information, or you enlarge the high k information. And the effect of Rj means the distance between absorbing atom and backscattering atom will like this, 1.8 angstrom, and here you divide it by this, your amplitude will be decreased. Okay, and the Debye factor, this one, this value, this is sigma square. If this value become a positive, the curve will become like this. With k increased, the intensity will be increased. But if this value is negative, the k increase will become decreased. So this, because there's a minus in front of the k square. So this sigma square should be a positive value, so that you can get with k increased, the intensity decreased. But if once you fit in, you obtain the sigma value is negative, then it will become the curve will become like this, so that it's not. This will tell you this is not correct. Now here is when you want to do, we just mentioned the spectrum. Once you will from K space, we will do Fourier transform to R space, and the range which you choose will also influence the resolution. Here I just want to show you, if you use the K range only, you can see this figure, K only 1 to 2, you do Fourier transform, you just a very broad peak. If you have a K from 1 to 15, and you got a sharp peak. So this will influence your data analysis. And this is also the same. Before, in this figure, you don't include the phase shift effect. But in this one, in the next, we include this. So you're 1 to 2, 1 to 2, and you go to 1 to 10, you have, and up to 1 to 15. And the reason why I choose this one is just because quite often for experiment, for theoretical, you can always up to k equal to 20. But for experiment, quite often maybe you can 1 to 10 or even a little higher. But try to up to k, obtain k up to 15 is still very difficult.